All right. So let me recall what we proved yesterday. Was there result that if V is a finite dimensional vector space, say of dimension n over a field F, and if T is a linear transformation on V, having all of its characteristic roots in F, in that case, T is triangular. That means matrix of T with respect to an ordered basis B is triangular, particularly lower triangular. That's what we proved. We further proved that in such a situation, T will satisfy a polynomial of degree n over F. And the polynomial that we proved satisfied by T is fx equal to x minus a11, x minus a22, x minus a and n. And if you see that the matrix of T is a11, a22, a and n are the diagonal entries. So fx satisfies a polynomial x minus a11 times x minus a22 so on times x minus a and n, where aii for i1 to n are the diagonal entries. In fact, these are the eigenvalues of the matrix T with respect to this ordered basis B that can be proved, and more can be proved that if for any arbitrary triangular matrix, the elements on the diagonal are the characteristic roots of T. So we can observe therefore that these AIIs are actually the eigenvalues or the characteristic roots of T. And that's what we started also with, that A11 as the characteristic roots. So we can prove this observation. Observe that in the proof, if you recall, A11 was an eigenvalue. A11 was an eigenvalue of T. In fact, each AII is an eigenvalue of T. We can prove that in general, we can prove that if A is a triangular matrix, A is of order n by n, let us say is this say alpha ij n by n is triangular and has all of its characteristic roots in F. This A, treating A as the linear transformation, then each entry, each alpha I is a characteristic root of A. A can be treated, the matrix A can be treated as a linear transformation on V over F. V is Fn over F. Defined by, you can say, linear transformation, let us say T. Defined by T is going to V, and every V going to Vt. Vt is Va, the product. So this is N by 1 by N, and this is N by N, and the product is 1 by N. An element here in Fn. And the matrix of this T with respect to the standard ordered basis is actually A. That also can be seen. So you can prove easily that if A is a triangular matrix, then each entry on its diagonal is the characteristic root. So what do you see here is that, so suppose this is the diagonal entry. So in general, let us say lambda. So for this, suppose lambda in F be some alpha I or I1 to N. Then A is triangular. Implies your lambda I minus A. So is also triangular. Is also triangular. The diagonal entries will be so lambda minus A11, lambda minus A22, and so on. So this matrix is also a triangular matrix. And therefore this here is singular. And this matrix can prove is singular. And lambda I minus A is singular. Now this is singular means lambda is a characteristic root. We have proved earlier that lambda is a characteristic root of T if and only if lambda I minus T is singular. So lambda is a characteristic root of a linear transformation. The converse also holds true. So suppose lambda is a characteristic root. Lambda in F is a characteristic root of A. Then this will force that the linear transformation lambda I minus A is singular. And therefore, one entry on the main diagonal must be 0. And that will force that at least one entry on the diagonal is 0 in the diagonal of this matrix is 0. So diagonal entry of lambda I minus A is 0. That means lambda minus AII is 0 or some. So lambda minus AII is 0 for some A or alpha we have written. For some I 1, 2 up to n, that means lambda is alpha I for some I 1, 2 to n. Or that means that lambda is a diagonal entry. A diagonal entry. So we have proved that the AIIs that appear in the polynomial satisfied by T, say fx x minus A11 minus times x minus A22 and so on up to x minus A and n. So AIIs are the characteristic roots of T, and this polynomial therefore can be written as x minus lambda 1 times x minus lambda 2 and so on x minus lambda n. So you can call lambda I to be the AII. And so if for the dimension of the vector space V over F is n, and if T is a linear transformation here, has all of its characteristic roots in F, then T satisfies a polynomial of degree n. And what is this polynomial fx? And write also x minus lambda 1, x minus lambda 2, x minus lambda n. So I have called lambda I AII. And where these entries, where the entries lambda i's are the characteristic roots of T. Good. Now suppose T has all of its characteristic roots NF, and suppose all of them are distinct. All of these lambda 1, lambda 2, lambda n are distinct. Where what is n? N is the dimension of V over F. If Vi is a characteristic vector of T with respect to the root to say lambda I, V1, V2, Vn are linearly independent over F. In fact, if you collect all of them, B consisting of V1, V2, and say Vn is a basis for V over F. And this basis is called an eigenbasis. It's called an eigenbasis. And if you put them in this order, then this is the ordered eigenbasis. For V over F. So what we can see therefore for a linear transformation, the matrix of T with respect to this basis, say B. So what happens is that now let us take dimension of the vector space V over F be n, finite, and B1 say is a basis, say U1, U2, UN, U1, U2, UN be a basis for V over F, and in this situation, and let us take B to be V1, V2, say Vn, be an eigenbasis for V over F. And T is a linear transformation. T be a linear transformation only. And let us say the matrix of this T with respect to B1 is A, and the matrix of T with respect to the ordered basis B2, say B, and S, let us say, be the linear transformation V to F, which maps Vi to Wi, sorry, Vi to U. Each Ui to Vi, and S. So if you now see what is this happening here, so the Vi is UIS. So if you want to write the matrix of the linear transformation S, then this is the matrix of the change. So SB1 is the matrix C is the matrix of transformation or change of basis. All of them are related by that B is CAC inverse. This is what we have proved. The matrix B is interesting in this situation if this is an eigen basis. You can see that the matrix of this T with respect to the eigenbasis is interesting. So TB2, B the TB2. So you need to write what is V1T, V2T, V and T in terms of, observe that each VIT is lambda IVI for I1 to N, and that gives that the matrix of T with respect to the ordered basis B2 is, so when I is 1, this is lambda 1 V1, it's the same as lambda 1 V1 plus 0 V2 and so on 0 Vn. So that gives the first row, and the first row becomes therefore here lambda 1, and all other entries are 0, 0, 0, 0. When you put I is equal to 2, in that case V2T is lambda 2 V2, which is same as 0 lambda 0 V1 plus lambda 2 V2 plus 0 V3 and so on 0 Vn. That gives you this. And like that, when you continue, you'll get, and this is lambda n by n by n. Okay. So this is lambda n के लिए फिर जगह नहीं है. So this is a diagonal. Is a diagonal matrix. Hence, correspondingly, if T has n distinct and linearly independent characteristic vectors, or that happens characteristic roots, then definitely it will happen if characteristic roots are all distinct. So if it has n linearly independent characteristic vectors, in V over F, where n is the dimension of the vector space, then T is not only triangular, T is diagonal. That means there exists a basis with respect to which the matrix of T is a diagonal matrix. This definitely happens if T has all the if all the characteristic roots are distinct. So if a linear transformation, or for that matter, if the square matrix A of order n by n has n distinct characteristic roots, then it has n linearly independent vectors, and they form a basis with respect to which the matrix of T is singular, is similar to a diagonal matrix. TB2 is diagonal. So that amounts to say that A is similar to a diagonal matrix, or A is diagonal matrix. Now, obviously, we would like to see that under what conditions a linear transformation is triangulizable. That means so it's does there exist a basis with respect to which the matrix of T is triangular? And we had seen if T has all of its characteristic roots in F, then it happens. We in fact would like to know further that is it diagonalizable? That means does there exist a basis with respect to which the matrix of T is a diagonal matrix? So that also, as we have discussed just now, is the situation when T has all of its characteristic roots in F, and if they all are distinct, then also we can see that there is a basis, namely the eigenbasis, with respect to which the matrix of T is a diagonal matrix. But does it mean that every time it happens? No, definitely not. There are linear transformations which are not diagonalizable. We had already seen an example. The matrix version is correspondingly for matrices. A matrix is similar to a diagonal matrix, and we say that A is diagonalizable if there exists an invertible matrix C such that CAC inverse is diagonalizable. So a matrix, the matrix A in M and F is said to be diagonalizable if there exists an invertible matrix say C in M and F such that CAC inverse or P inverse AP, where P could be C inverse, or P inverse AP, is a diagonal matrix. So as just now we had seen that this happens if A has all of its characteristic roots distinct, then this happens. But this all discussion is based on the assumption that T has all of its characteristic roots in F. But that may not happen always. Now let us take the matrix here. Now consider this matrix. A, small matrix, 2 by 2 only. And let us take this as M and F, where F is, let us say, real numbers. Or you can see quite interesting situations. If you want, you can also take the linear transformation and say T, say R2 over R, is R2 over R to R2 over R. So this takes any vector, say V, say XY, VT, VT is say VA, and this is XY, and this is A, 0, 1, minus 1, 0. And you can see that this is basically, so this is X times 0 is 0, and then this is minus Y, this is X. So what is the map that we have defined? This. And you can see that this map is actually a linear transformation. Then T is a linear transformation. And also you can see that the matrix of T with respect to the ordered basis B, where B is the standard ordered basis, so 1, 0, 0, 1. With respect to this, the matrix of this is actually A. You can prove easily, that is not difficult. So either way, now what are the characteristic roots of T? Characteristic roots of T or A, whatever you want to say. So roots of T. So suppose lambda is a characteristic root of T. Then there exists a non-zero vector, say V, say X, Y, and V such that Vt is equal to lambda V. That makes Vt is what? Minus Yx is same as lambda times Xy. So this is lambda X, lambda Y. And equality of these two says that minus Y is equal to lambda X. So lambda X is minus Y, lambda Y is X. Nice. So what, and X and Y, both of them at the same time are not zero. Now you can see that here XY is not 0, 0. X and Y both are not 0 at the same time. So what are the possible values for lambda, or what equation does it satisfy? So if you see this, if you multiply, this is both sides. This is lambda square xy, and this is lambda square minus. So this implies multiplying both. So lambda square xy is minus xy. So lambda square plus 1 into xy, this is 0. Now x and y both at the same time are not 0. So if x and y both are not 0, then what will happen? Now you can see here that if x is 0, then y is 0, because if x is 0, then lambda x is 0. If lambda x is 0, then minus y is 0. That will force y is 0. So x cannot be 0. Likewise, y cannot be 0. Because if y is 0, minus y is 0, that means lambda x. So that will force that your x is 0. See what I'm saying is, here x cannot be 0. Otherwise, what will happen? If x is 0, this will imply lambda y is 0. Sorry, x is 0, lambda x is 0. So x is 0 means lambda x is 0. Lambda x is 0 means minus y is 0. Means y is 0. That means xy is 0, 0, if that happens. So this is a contradiction. So a contradiction. Here, this is not possible. All right. Likewise, when your y is 0, then lambda y is 0 and x is 0. A contradiction. So x is not 0. Similarly, y is equal to 0 also implies x is equal to 0. Again a contradiction. Hence, neither x is 0 nor y is 0 in this situation. And that forces xy is not 0. That forces lambda square plus 1x y is 0. So that will make lambda square plus 1 is 0. But then lambda does not belong to F. F is here R. So there are linear transformations or matrices whose characteristic roots are not in F. No characteristic root is in F. You can also observe that the minimal polynomial for this so no root is in F. So whatever discussion we have done was for the linear transformations whose all roots were in F, will give no more information. So we need to think about all such situations. Also observe that t here we are to or r, which was defined as xy, v going to vt as xyt minus yx. As it's a minimal polynomial, x squared plus 1. Since you can see that t square plus identity, when you apply, so since t square plus identity, when you apply on v, so this is vt square plus v and then I, so this is vtt plus v is what? So vt is minus yx. So for v is equal to xy t square plus I, this vt is here minus yx t plus xy, and this is x becomes minus y. So when you do it again, so this will be minus x minus y. And this is 0, 0. This is 0. That is v under t square plus I is 0 for every v in v. That makes the t square plus I is 0. So the minimal polynomial, and you can see that no linear polynomial is satisfied by t. So this is the minimal polynomial. We also know that the root of the minimal polynomial is a characteristic root. Now the problem is what to do with such linear transformations or matrices which do not have all of its characteristic roots in F. So what we do is we take the splitting field of this polynomial. So now let T be a linear transformation over a finite over a field, say F, and dimension of V over F, let us say n be finite. And let us say your Px will be the minimal polynomial of T. Over F. Then all the roots of Px may not be in F. If all the roots are in F, we could use whatever we have learned so far. So we take K to be the splitting field of Px. That means K contains F and K is the smallest. K is the smallest field containing all the roots of Px. So Px could be treated as a polynomial over K because any element in F is also an element of K. And in that case, all the roots of Px will be the roots of all the roots of Px will lie in K. So if P naught x is the minimal polynomial, so all the roots, so all the roots of Px will lie in F, in K, sorry. They may not lie in F, but they will lie in K. The polynomial Px can be treated as a polynomial in Kx. So all the characteristic roots also will lie. Because a characteristic root, so all the characteristic roots of T will lie in K. So we can therefore use our knowledge over K. Now this T can be treated as a linear transformation over K, or its matrix version, which is rather easy to understand, can be considered as a matrix over K. If it is a matrix over F, the entry is coming from F, so they are entries from in K also. So if A is the matrix of T with respect to some ordered basis B is in M and F, then this is definitely is in M and K. So this matrix can be thought of as an element of M and K. So all the roots of so all the roots of Px, the minimal polynomial of A, and therefore all the characteristic roots of A lie in K. So that is the matrix. So this matrix A can be treated as a matrix over K, as K is a bigger field. The roots will lie in K. The minimal polynomial of if P naught x in Kx is the minimal polynomial of A, then P naught divides every polynomial satisfied by A. And A satisfies the polynomial with coefficients in F, namely P. So this P naught x, therefore, in particular should also divide this Px. So all the roots of the minimal polynomial of A are the roots of Px being the root of P naught x, as P naught x divides Px. So what we get here is that all the roots are the roots of Px. So they lie in K, because all the roots of Px, they lie in K. So we have got that all the roots of the minimal polynomial of A lie in K. And every characteristic root, therefore, is a root of the minimal polynomial. In fact, for an extension K, which you can take as the splitting field of the minimal polynomial, a root of the minimal polynomial is a characteristic root, and a characteristic root is a root of the minimal polynomial. So here, as we have done earlier, that assuming that all the roots of the characteristic, all the roots of the minimal polynomial lie in F, will mean that all the characteristic roots lie in the splitting field of the minimal polynomial of T, namely Px. Okay. So henceforth F will be replaced by the splitting field of the minimal polynomial, where all the roots will lie. Characteristic roots become the roots of the minimal polynomial. If all of them lie in F, so F is now replaced by K, the splitting field of the minimal polynomial Px. This all is to accommodate the situation when the characteristic roots are not. Now we quickly come to this interesting observation that what happens in particular situations. So canonical form means is a form which is beautiful to see. That's all I think I can say. And the particular linear transformations having particular forms are of interest. So this is one result that we shall prove, and then we shall wind up for today. So we shall be doing nilpotent linear transformations, so canonical forms. To begin with, we shall have nilpotent linear transformations to start with. A linear transformation is said to be nilpotent. So T is a linear transformation. AFV is said to be nilpotent if T to the power K is 0 or some positive integer K. And if this K is least, then this is called the nilpotency index. If K is least, then it is called the nilpotency index. Right. So we want to see, does there exist an ordered basis with respect to which the matrix of T is somewhat beautiful? And if so, then what is that form? This is what we want to find out. So what we want to prove is this result for today. We can see it quickly. So if V is a finite dimensional vector space and V is the direct sum of so this is one theorem that we are proving of say Vk, where each Vi, the subspace, is of dimension Ni. So dimension of Vi over F is Ni and is finite. And this Vi is T invariant. You remember T invariant means that Vit is contained in Vi. Where T is some linear transformation for AFV for each I 1, 2, K. Then there exists a basis so B for V over F such that the matrix of T with respect to this ordered basis B is an interesting matrix. This matrix is a matrix which consists of this A1, 0, 0, 0, and say 0. 0, A2, 0, 0, 0, 0, and like that. 0, 0, 0, zeros, and AK. N by N. Where N is the dimension of V over F and is same as V1 N1 plus N2 plus N. And what are these matrices? And AI is the matrix of TI, and TI is basically this is Ni by Ni, Ni by Ni, and Ti is the restriction of T on the vector space Vi. This is what it is that you want to prove. Let me see the time now. So the time is, oh, it's already 9, so that doesn't make sense to push the proof. So we shall take up from here. So we shall prove next time when we meet this result, and then proceed to see some canonical points. So thank you very much for today, for your kind attention and time.
Thank you, sir.